I had a bunch of different distractions in first period. It didn't feel, my lesson delivery didn't really feel very organic. So this one will be better though, for sure. Hey, one great thing about calculus is not only do we learn how to take like all these crazy derivatives, but we also learn how to use them and what they mean. And that's one of my favorite parts about calculus. Like, I've always been pretty decent at math. And so like through algebra 1 and algebra 2 and like pre-calc and stuff like that, I didn't really have to apply myself. But then like once I got to calc, like this class kicked my butt. And it was particularly when we got to like practical application of calculus, because I like, spend a lot of time in it in the classes like leading up to this. You guys do here at Revere because you guys have a really good like supplemental classes leading up to calc. But in my experience, I didn't really spend a lot of time doing practical application until I got to calculus. So then once I got to those problems, it was kind of tough for me. So, but I like it because now I realize like, hey, this is cool because like this stuff is applicable to our everyday lives. We can, and you can very easily see how like the impacts of calculus have shaped like the society that we live in today. Okay. All right. So we're going to start dipping our feet in the pool of practical application of derivatives. Today's not going to be practical application in the terms of like, talking about like liquid in a tank or something like that, like we did on the test. We're more going to talk about like what derivatives mean and how we can use them. Okay. Now, what does a derivative tell you? Like in a very general sense, a derivative tells you what? Slope of a tangent line. And then on test, you guys also talked about rate of change as well too, right? So if my slope of my tangent line is positive, what would that mean about my function? Or if I have a positive rate of change, what would that mean about my function? What is my function, my original function, doing? It's increasing. What about if I have a negative rate of change? Decreasing, right? So we've talked about that, I think, in passing, but we've not really done much with it. That's what this section is for. So if you have a positive rate of change, your function's increasing. If you have a negative rate of change, your function is decreasing. What about if your rate of change is 0? What's your function doing? It's not changing, so it's constant, right? Good. And that's what this next slide shows us, okay? This very zoomed out next slide. So now we've studied several types of derivatives in depth. We can actually start using them in application. Here we have an increasing function. And if we very quickly sketch what our tangent lines look like in this case, like our little tangent lines going along our graph here, we have, you guys would obviously be able to see we have some positive tangent lines on our graph, okay? That's because our function is increasing. So if x1 is less than x2, then f of x1 is less than f of x2. And moreover, our derivative is positive. That's the important part. You're the best. Thank you.
Thank you.
How'd you do it, Anya? Did you say probably bad? Or were you answering her question? How'd you do? Some good looking stuff on here. Okay, and then for our middle graph, we can see it's decreasing, it's going down. And if we sketch our tangent lines in there, we would find that all of the values of our tangent lines are what? All of our tangent lines are negative, right? Okay. All right, so if x1 is less than x2, then f of x1 is actually greater than f of x2 because your outputs are going down. And then the value of your first derivative is then negative. And then, like you guys told me, if your function is constant, then that would mean that your derivative is equal to 0 over that entire domain, okay? So f of x1 would equal f of x2, okay? So what I'm going to do is I'm going to give you guys a function, and I'm going to say, hey, tell me where your function is increasing and tell me where it is decreasing, okay? In order to figure that out, we need to figure out where the value of our derivative changes from positive to negative. What happens on a graph as you go from a positive value to a negative value? What are you doing? It's equal to 0, or it's crossing your x-axis, right? So what we're going to do in order to figure out where our functions are increasing and decreasing is we're going to take our derivative and set it equal to 0. And then we'll use those values to set up intervals, and we'll test the value of those intervals in our derivative to see whether it is positive or negative. If your derivative is positive, you're going up. If your derivative is negative, it's going down. Okay, so that's what this paragraph from me rambling on says. We test a function for intervals of increase and decrease by setting your derivative equal to 0, and then using the zeros slash discontinuities of both your original and your derivative to break the domain into intervals. We then pick test values from those intervals to plug into our derivative. The sign of the derivative in that interval tells us whether the original function is increasing, decreasing, or constant. So one thing you keep in mind is that you're using your derivative to tell you information about your original function. Okay, so we're using our derivative to tell us things about our original function. Okay, all right, and then if I, just do a little sketchy sketch of something that looks like that, for example. How many values of our derivative appear to be 0 on that graph there? 2, right? So it looks like at x equals 0, we have a horizontal tangent, and also here we have a horizontal tangent, okay? So we could say like the value of our tangent lines, what am I doing? I need to be writing in gray. It's gray day. iPad says, no thank you. You know what I wanted to do? I wanted to wear like nice gray dress pants, a gray button-up shirt, and a gray tie, and go like full teacher outfit. I thought I'd have to like run at the bank after school or something, and then I would just like walk in like gray on gray, and like, yeah, all right, next time I will. I like the color gray. Gray is one of, I don't know. I don't know. I don't know. You're right. I need to full commit.
All the TV, no. So you can be a biker or a surfer on Friday. Sorry.
Unfortunately, I won't be here on Friday.
Oh, why not?
I have to take the day off. Oh, is it? Gotcha. Have not seen it.
You can still dress up for it, even if you're not.
Yeah, I'll let them.
Yeah.
Whatever you have.
Dress up at home? Okay. Yeah, I'll be at home that day. There's a doctor's appointment, so it's okay. No, it's okay. It's not for me, but all right. So the other thing, so like our first derivative tells us things about our original function, increase, decrease. We can also learn information about our original function by looking at our second derivative. Now, increase, decrease, that's a pretty easy concept for sure. Have you guys talked about concavity in a math class? Concave up, concave down? I know you've heard that word before, concave, right? What on my face is concave? Yeah, my eyes and my glasses are concave because my eyes have concavity with them as well too, right? So when we talk about concavity, that's roughly the shape that we're talking about, okay? So our first graph here is what our graph would look like if it was concave up, okay? So a couple things to note. First of all, your derivative is increasing. So if your derivative is increasing, then our function is concave up, okay? Now, what I usually go off of if I'm visually trying to determine if my graph is concave up or concave down is this part right here. Your function will lie above its tangent lines. So if I sketch those like little tangent lines in there, I want you guys to see that my graph is above my tangent lines. Okay? You can almost think of it like if your graph is concave up, if you spilled a glass of water in there, it would hold the water, okay? Which you can see, like, this whole graph is concave up on this interval that's shown. If I spilled water in here, it would hold this water in like a basin, okay? But moreover, I figured out if I have a function by saying if my second derivative is positive, then it is concave up, okay? Whereas concave down looks something like this, okay? The value of my derivative is decreasing, and I'll talk about that here in a second. So if I draw some derivative values in there, it is decreasing. And then I could say that my function lies below its tangent line. So like here my function is above its tangent lines. Here my function is below its tangent lines. Okay? And if Stella, my middle daughter, spilled her cup of water, as she often does, it would just spill all over this function. It would run off. Okay? So your function would spill water in that case. Well, I use that phrase like loosely, though. We'll look at some examples of that. But if your second derivative is negative, then we say it is concave down. Now let's talk about derivative increasing, derivative decreasing. So if I look at the values of the derivative for my first function, I've got negative values here, but you see those negative values are getting close to 0. And then on the other side, my values are then going to be positive. And they're positive and getting steeper as I go to the right. So like the slope of my tangent line would get steeper as I kept going, okay? So that's how you can tell my derivative is increasing. I have negative values, and then it's reaching 0, and then I have positive values. Whereas my function to the right here, your derivative is decreasing. I've got negative tangent lines here that are getting close to 0, so 0 here. And then on the other side of that, I have positive tangent lines here getting close to 0, and then on the other side I have negative tangent lines. So we would say that our derivative is decreasing, okay? Now, to test for concavity, pretty much the same method as testing for increase, decrease, except you take your second derivative and set it equal to 0, and then you set up intervals and you test those intervals, okay? So I want to show you what that looks like, okay? Now, when our function goes from increasing to decreasing, let's talk about what type of value we have on the graph. Hey.
Hello.
Welcome. Nice grout fit.
Thanks.
I don't know why I took that. Just did that. We did pretty good on the gray on gray. We might have to take a class gray pick after this, if there's time. Ved does have gray pants on. Well done, Ved. 50% gray. If I take this off, I'm 50% gray too. So maybe I'll just button this up. All right, but either way, when we talked about increase, decrease, where my function switches from increase, decrease, that's like here. What would we call that red dot? What graphical feature is that? You said what? I wouldn't necessarily call it a vertex. I understand why you say that, though, like vertex of a parabola kind of looks like that, right? Local maximum. So local max, relative max. It is also the y-intercept. I felt as soon as I said that, I was like, actually, I should switch it to this one. All right, what about this one, Soph? What's this one? Oh, local minimum, right? So our function switches from increase to decrease. One of the places that happens at are local maxes and local mins. We'll talk about that next section. When my function switches concavity, that happens at what is called an inflection point. Now, let's talk about this graph. Whereabouts would this graph switch from concave up to concave down or vice versa? So like, what about this left side of the graph here? Would you say this is concave up or concave down? Down, spills water, right? Lies below its tangent lines. And then somewhere here, concave up, right? So somewhere between these two parts of the graph is where it switches concavity. It's tough to visually see, but I would say like somewhere around right there. Would you guys agree? So that is what we would call our point of inflection, because that's where it switches from concave down to, in this case, concave up. Okay? So we would call that our point of inflection. All right. Can I show you how to do that stuff? Please? All right. Here we go. Okay. We're going to start slow. We're going to start small and easy. Okay? And then the last example we do today will be pretty intense, but we're going to start small. Okay? How do I sit here so I'm not in Ved's way? I'll do this. I don't know. I feel like I need to sit on the desk. Okay, so I want to first determine where our function is increasing or decreasing. Okay? So in order to do that, what tells me that information, whether it's increasing or decreasing? Slope of my tangent. Yep, so I got to look at my first derivative. Okay? Kira, here's what you missed really quickly. If I want to figure out where my function is increasing or decreasing, I need to look at the value of my derivative. So like here is an increasing function, right? Do you see how all of my tangent lines are positive that I drew in there? That means your function's increasing. It's decreasing if you see all these tangent lines are negative, right? So if the value of your derivative is negative, it's decreasing. The value of your derivative is positive, it's increasing. If your derivative is 0 consistently on an interval, then we'd say it's a constant function. okay? So if I want to test where my function is increasing or decreasing, I take my derivative, right, slope of the tangent line. I take my derivative and I set it equal to 0. And then I'm going to use those values to set up intervals of increase, decrease, okay? All right, so by now you guys have taken your first derivative, which is what? So I want to set that equal to 0. That's going to become commonplace, is setting your first derivative equal to 0. We're going to do that in a lot of different parts of this class, okay? So when you do that, you get x equals what? Add 4 to both sides, divide by 2, and you get 2, okay? So 2 is the number that I use to set up my intervals of increase, decrease, okay? Now, my original function f of x is a polynomial. So its domain is all real numbers, right? Okay, so then my interval should reflect that. I would do negative infinity to 2, and then from 2 to infinity. Okay, so I take the zeros of my derivative, and I set up intervals with those values. Now what I want to do is I want to test those values and see whether they are positive or negative in my interval, okay? So I'm going to move this over to the side a little bit. All right, can I get gray yet? Why is that not working? Bummer, dude. Sorry, guys. I had intentions of going gray, but... All right, so now these values in the interval, I just pick a number that's between negative infinity and 2, and then I plug it into my first derivative. If my first derivative is positive, it's increasing. If my first derivative is negative, it's decreasing, okay? All right. So, from negative infinity to 2, what number do you want to plug in?
0.
Easiest one. If you plug 0, now I'm plugging it into my first derivative. So 2 times 0 minus 4 gives me negative 4, okay? Which means my function is negative. My first derivative is negative on that interval, okay? All other values will be negative, okay? Because I already charted out my x-intercepts, and that's where it switches from positive and negative is on either side of the intercepts. I already charted them out. So everything from negative infinity to 2 is going to be a negative output in my derivative. All right, so then on the other side of 2, what do you want to plug in? Super. F prime of 3 equals 2 times 3 minus 4. So 6 minus 4 is going to give me 2, meaning positive values. Okay? So if we interpret what that means, we could say that our function is increasing when x is an element of 2 to infinity. And then we would say it is decreasing when x is an element of negative infinity to 2. All right. Now let's do concavity. If I do concavity, which function am I looking at? I do my second derivative, right? Okay, so I need to take f double prime of x and let it tell me things about my function. Now, what is my second derivative? 2. Okay, can I set that equal to 0? No? So it gives me no solution, right? However, I still need to test an interval. What's the interval I'm going to test, though? Negative infinity to infinity. I'm just going to test the whole real line because my concavity does not change, okay? Any number that you try to plug in, there's no real place to plug it in, right? What is the output of your second derivative always? 2. So what type of value?
Hey, pardon this brief interruption.
Positive, right?
I usually like to get on right after the phone, but I was tied up for a second. This is for all seniors, and the reason I'm doing it now is because we have a number of seniors who leave after this period. Senior sunrise tomorrow. We are just going to plan like the morning is going to be like it has been the past couple days, and we are going to move inside. It's no longer at 6:45. We're going to do 7 a.m. in the main gym. We're just going to have kind of a fun atmosphere for everybody to come and join.
Hold on, listen up.
As we continue on during this year, we will also have donuts and all the good things, and then we will go to the seniors. Please bring your iPad. All right, if anything changes, we'll just move outside.
They pulled Rhea out last period and talked to Rhea about it. So I had a feeling this was coming. I don't want to be the one to tell you guys, but senior sunrise is such a cool idea. It's a bummer that it landed on a day like tomorrow. I think they're gonna do a drone picture later. I think is what I heard them say. Like another day, maybe. It's a good question, Max. I don't know. All right. So my second derivative, I'll play a video of a sunrise for you guys when you come in. Hopefully they do that for you guys. I don't know, something for you guys. Projector maybe?
2 years ago, that's what they did.
I don't know. We'll be positive about it, right? Right? All right. Okay. From negative infinity to positive infinity, we find that our outputs are positive, which means our second derivative would be concave up or down? Concave up. So concave up when x is an element of negative infinity to positive infinity. Because our second derivative is positive. So Kira, yeah, you probably missed that concavity part as well too. When your first derivative is positive, it's increasing. When your first derivative is negative, it's decreasing. When your second derivative is positive, we would say it's what's called concave up. And then when your second derivative is negative, it's concave down. If I go back to last slide, this is what a portion of a graph that's concave up looks like. Not all these extra, like, the mess on there that looks like a football play. Bunch of X's and O's. But this is concave up because it lies above its tangent lines. If I drew a bunch of tangent lines in here, it's above its tangent lines. So we'd say it's concave up. Your second derivative is positive on this interval. And then over here, this is what it looks like, it's concave down. Your second derivative would be negative on this whole interval because your first derivative is decreasing and your function lies below its tangent lines. Okay? All right, let's do another one. Another polynomial. We'll do 3 polynomials, and then we'll do something that's much more difficult. Okay? All right. Given f, find the same thing. Let's find where it's increasing, decreasing, and then determine concavity. So we start by doing what? I'm really annoyed that I can't choose the color gray. It's a bummer. All right. First derivative. Green it is. 12x cubed plus 12x squared minus 24x. Okay. I do want to set that equal to 0, but what can I do with it? What could I... Yeah, let's factor 12x out. So then we have x squared plus x minus 2. But we can factor the inside of that, right? It would be x plus 2, x minus 1. Oh, thank goodness it factored. Okay, so then if we set each one of them equal to 0, how many zeros do we get? Yeah, so then that gives us x equals -2, 0, and positive 1. Okay, if I list them in numerical order. So then those are the values that I want to use to set up my intervals. Again, my original function is a polynomial, so its domain is all real numbers. So then I would have, I want to test from negative anytime it switches to crayon, that's like the equivalent of like Comic Sans. All right, negative infinity to -2, -2 to 0, 0 to 1, and then 1 to infinity. So I want to test a value in each one of those intervals. And again, I need to determine the sign of my first derivative. I don't think I really exemplified this in the last lesson. I don't care what the specific output of your first derivative is. I just care whether it's positive or negative. It's the only thing that matters to me, okay? So if we don't find an exact value, I don't really care about that, okay? All right, what do you want to test between negative infinity and -2? Negative 3 is a good one. Let's do that. So if I plug negative 3, now I'm going to plug it into my first derivative. We have to be very careful about how I do that. I don't want to plug it in to this form right here, because then I have to like cube it and combine it and really figure out if it's positive or negative. I think it's much easier to plug it into this factored form, okay? And as long as I didn't get rid of any values or divide by any values that went away, I can still plug it into a form like that. So if I plug in negative 3, for 12x, I would get a negative value times, if I plug it into this middle set, it would be negative 3 plus 2, which is negative again. And then if I plug it into my last set, negative 3 minus 1 is also a negative number. So a negative times a negative times a negative is what? Negative. Okay. What about from negative 2 to 0? Probably negative 1, right? Okay, so if I plug it into my derivative, negative 1 times 12 is going to give me a negative value, times negative 1 plus 2 is positive. So negative times a positive times, and then negative 1 minus 1 is also negative. So negative times a positive overall gives me what?
Positive.
Very good. Okay, and then from 0 to 1, half, I guess. So then half of 12 is 6. A half plus 2 is positive, so positive times a positive. But a half minus 1 is negative. So I would have positive times negative, giving me a negative value. And then last but not least, let's plug in 1 million. So if I do 1 million times 12, I get a big positive number. 1 million plus 2 is a big positive number. And then 1 million minus 1 is still a big positive number. So a positive times a positive times a positive gives me what type of output? Yes. Okay, so we would say that our function is increasing when x is an element of negative 2 to 0 unioned with 1 to infinity. And then we would say it is decreasing when x is an element of negative infinity to negative 2, unioned with 0 to 1. Okay? You with me there? Okay. Now, let's do concavity. All right. So then f double prime of x would be, so I look at this, try to figure out what my second derivative is going to be. 36x squared plus 24x minus 24. All right. We can factor that a little bit, right? What can I at least take out? 12. So I have 3x squared plus 2x minus 2. Is that factorable? I know 3x squared plus, or maybe it's something like 3, 2, and 1. I know those coefficients are factorable. But 3, 2, and negative 2, not factorable. We can't factor that. But I still need to set it equal to 0. So what should I do? I should indeed do the quadratic formula with this right here. Okay, so, and it's easier to use the coefficients when 12 is already factored out. So negative b, negative 2, plus or minus square root of b squared, so 4, minus 4 times a, which is 3, times c, which is negative 2, all over 2 times my a value, which would be 3. All right, negative 2 plus or minus square root of, okay, 12 times 2 is 24, so 4 plus 24 would give me 28 over 6. All right. Okay, so then now I can actually simplify square root of 28 a little bit. I can pull a 4 away from the 7, take the square root of 4 and make it a 2 outside that square root. Do you guys remember how to do that really well? Extracting roots. Okay, so then that would give me negative 2 plus or minus 2 square root of 7 all over 6. And I can reduce each one of them by a factor of 2. So then 1, plus or minus, or negative 1 rather, I'm sorry, plus or minus square root of 7 over 3. Okay. So those are going to be the values that I use to set up my intervals. So then I would do negative infinity to negative 1 minus square root of 7 over 3, negative 1 minus square root of 7 over 3, to negative 1 plus square root of 7 over 3, and then negative 1 plus square root of 7 over 3 to infinity. Okay, those values aren't very pretty, but we can still do it. We got this. Okay, I feel like it'd benefit us to figure out roughly what that is around. So like square root of 7 is somewhere in between 2 and 3, right? So if I do negative 1 minus 2 point something, that would give me like negative 3 point something divided by 3. So this would give me like negative 1 point something. Okay. And then negative 1 plus square root of 7 over 3. So it'd be negative 1 plus something that's in between 2 and 3, which would then be something in between 1 and 2. And then divided by 3 is going to give me like 0 point something. So positive 0 point something. Okay. So I just need to make sure when I test values, it's between those values. Okay. So if I didn't have a calculator, I can still do it. So f double prime of x, let's see what our sign is. What do you want to test? It's in between negative infinity and negative 1 minus square root of 7 over 3. Negative 2? Okay. Now, I need to plug it into my second derivative. I guess I'll plug it in here. So let's see. Negative 2 squared is 4 times 3 is 12 plus 2 times negative 2 would be minus 4. Minus 4 minus 2 is still going to give me a positive number, and then I'm going to multiply it by 12. So this is positive. Okay, what can I plug in between these values here? Oh, thank God. That's so much easier. All right, if I plug in 0, I would get negative 2 times 12, which is negative 24. So negative there. And then I need to plug in something between negative 1 plus square root of 7 over 3 and infinity. So something bigger than 0 point something. What do you want to plug in? Let's plug in 1. So 3 plus 2 is 5. 5 minus 2 is 3. 3 times 12 is going to give us a positive number. Again, I don't care exactly what the output is. I just want to know the sign. Is it positive or is it negative? That's the only information I need. Okay? So that means I'm concave up when x is an element of negative infinity to negative 1 plus, minus square root of 7 over 3. Unioned with negative 1 plus square root of 7 over 3 to infinity. And then concave down when x is an element of negative 1 minus square root of 7 over 3. What? And then negative 1 plus square root of 7 over 3. All right. Get used to this process because we'll be doing this same process on problems for the next week and a half, probably. We're going to spend a lot of time on this. All right, let's do one more polynomial, and then I got a special treat in store for you. What's our first derivative? Yeah. If I set that equal to 0, what's my x value? Okay. So then I get x equals 0. So then that means my interval is just negative infinity to 0 and then 0 to infinity. So I need to test my first derivative and see what the sign is. All right. What do you want to plug in between negative infinity and 0? Sounds good. Negative 1 squared is 1. 3 times 1 gives me 3. I get a positive output. Great. What about between 0 and infinity? What do you want to test? Positive 1. So 1 squared is 1 times 3 is positive 3. Uh-oh. What's that mean? It's just increasing. Okay. When a situation like that occurs, you need to be careful about what type of function we have. Now, it's x cubed. Is that a continuous function? Yeah. What happens right around 0? What does the graph do? With your finger, trace what x cubed looks like. Kind of just like stalls a little bit, right? At 0 and then continues on its way. So I would say it's increasing from negative infinity to positive infinity. If there was a vertical asymptote, then I would say at like 0, for example, we'll get to that stuff later. I would say it would be increasing from negative infinity to 0 and then from 0 to infinity. So like if there was like some sort of undefined value, I would need to keep those intervals split up. But think about the nature of x cubed. I'm talking negative outputs, it hits 0, and then it's going to go to positive outputs. So it is fully increasing on its whole domain. But in situations like this, we need to be more careful, or we need to be careful. Max, what's up?
Isn't it not increasing at 0? It's like the slope of 0.
Well, okay, so we can all call it this to kind of like, I guess you're right, at 0. But if you look at like, when we defined increase decrease, we said that f of x sub 1 is less than f of x sub 2. So it would constantly be increasing that whole time. When we talk about increasing decreasing, I didn't mention this yet, but we usually talk about it on an interval instead of at a specific point, because at any one specific point, you could find the value of your derivative. But what we would call this is, and I've never heard this notation before, this is Mrs. G notation that I've adopted from her, but we would call this what's called a stationary point. So we have a stationary point in our original function at 0, 0. Because it kind of just like stalls at 0, 0 before it continues on its way. Okay? I've never heard of that notation before, so I'm going to credit Mrs. G for that one. All right. I've used my first derivative to its fullest extent. Now let's do our second derivative, which is just going to be 6x, right? Derivative of 3x squared is going to give me 6x. I set that equal to 0. Again, I get that x equals 0. So I use that to set up my intervals. So I would have negative infinity to 0, and then from 0 to infinity. So similarly, I want to use my second derivative to then tell me, is my function, in this case, concave up or concave down. So I need to look at the sign of my second derivative. So a number between negative infinity and 0, let's just plug in negative 1. If I plug it into my second derivative, 6 times negative 1 gives me negative 6. So that's my negative output. And then if I plug something in from 0 to infinity, plug in 1, 6 times 1 gives me 6. That's a positive output. So that means my function is concave up when x is an element of 0 to infinity. And then concave down when x is an element of negative infinity to 0. Okay, so again, first derivative to tell you your increase, decrease. Second derivative to tell you your concavity. Not only can we say we have a stationary point at 0, 0, what is 0, 0 in relation to our second derivative? What do we call that? Point of... Here it is. So we have a point of inflection at 0, 0. Because it switches from concave up to concave down. Okay. All right. Questions there? In order for something to be a point of inflection, it has to be defined in your original function. And it is. Okay. As promised, a nice little sweet treat to end the class period. X plus sine of 2x on the interval from 0 to 2 pi. Hey, real quick, what's the graph of sine look like with your finger? Hey, that's a lot of switching from increasing and decreasing, isn't it? Yeah, that's going to happen a lot in this problem. So this is a long problem. It's going to take us some time, okay? All right, but let's start the same way we start all the rest of them, by checking to see if the gray works, and it doesn't, so we'll just keep on going. F prime of x equals, okay. What's our first derivative going to be? 1 plus, What's that going to require? Chain rule. Yes. Okay. So sine 2x. I need to take the derivative of that. Okay. You want to think about it like u's and y's? Go for it. I would just think about it as I know I have to take the derivative of my outer function with my derivative or with my inner function still inside, and then multiply it by the derivative of that inner function. So the derivative of sine is cosine. So cosine 2x is still in there, but I need to multiply it by the derivative of 2x, which would be, so that gives, I'm going to put that in front of cosine. So 1 plus 2 cosine 2x, okay? All right, now I need to set that equal to 0. This is where the fun begins. Okay, so we have to solve that. So I would start by subtracting 1 from both sides. So then I would get 2 cosine 2x equals negative 1. And then divide by 2. So then cosine 2x equals negative 1/2. So your job is to figure out where cosine of 2x equals negative 1/2. Do we remember how to do that when inside of cosine is something other than x? No, that's okay. We did learn it in trig, of course, right? I'm confident of that. It's just been a minute since you guys have seen it. For the record, I wanted to put one like this on the test. But then I was like, we haven't done one like that in class, and I don't know how well they remember it from trig. So instead, I switched it to, instead of cosine to 2x, I think I made it like cosine of x or something like that. It was where you had to find the horizontal tangents. Yeah.
You started grading it in the high.
Was it
No.
like a, was it like you found the derivative and it's like negative side?
Really?
Something like that.
How are the grades looking?
They're looking. I have started grading it. It's fine. Everything's fine. It's all good. I came in a good mood today. It's all good.
Well, what do the scores look like?
So I don't have any scores yet because in both first and third period, I've graded everyone's first, second, and third page. Now I need to grade your fourth and fifth page. So that's the intense part. So, all right, here we go. Now, in order to figure out where cosine of 2x is equal to negative 1/2, we treat this as if inside of cosine was just x. We want to figure out where cosine is equal to negative 1/2, and then we'll go from there. Okay, so I'm going to draw myself a little unit circle off to the side. I'll probably do that again elsewhere. But what quadrants would I have a cosine value of negative 1/2? 2 and 3. So that would happen at x values like here, right? There and there. And how do I know that? Well, I know my coordinates are either square root of 3 over 2, square root of 2 over 2, or 1/2, right? Since I want cosine to be 1/2, cosine's my x-coordinate. Where do I have the lowest x-coordinate? That happens at this radian here. This radian over here would give me a larger x-coordinate, or the x-coordinate related to square root of 3 over 2, because it's more of a distance. I want it to be negative 1/2, okay? So that radian is what? What about down here? Good. So 2 pi over 3 and at 4 pi over 3. Now, instead of saying x equals 2 pi over 3 and x equals 4 pi over 3, I have 2x inside of my trig function. So I would do 2x equals 2 pi over 3 and 2x equals 4 pi over 3. Okay? And then I need to solve those little mini equations by multiplying both sides by 1/2 or dividing both sides by 2. So that would give me x equals pi over 3 for the first one. And then for my second one, I would get x equals 2 pi over 3 if I multiply it by 1/2. Are you guys okay with that? I didn't show that 2 canceling out, but I know you guys are capable of that. Now here's the thing. I want all of my solutions from 0 to 2 pi because they gave me that as an interval, which was nice. It was nice they didn't give me the whole freaking real line, right? I just need to do from 0 to 2 pi. But I only got a solution in the first and the second quadrant. So I can't help but wonder if there are more. There are. I need to compensate for the fact that it's 2x. So instead of just doing one trip around the unit circle, I need to go further and look at my coterminal angles and see if those will give me solutions as well too. Okay? So if I did 2 pi over 3 plus 2 pi, what coterminal angle would be right there? Let me know what 2 pi over 3 plus 2 pi if I do that off to the side? It would be 8 pi over 3. Good. And I'm probably going to need another one down here would be my guess. So 4 pi over 3 plus 2 pi would give me what? 10 pi over 3. Good. All right. Now, if I go beyond that, I would have to go like another whole trip around the unit circle. I don't know if I'll get one there. Let's see what we get here. So if I do 2x equals 8 pi over 3, and then 2x equals 10 pi over 3. Let's just solve those real quick. All right. So I would have to divide both sides by 3. Or I'm sorry, divide both sides by 2 or multiply by a half. So I would get x is equal to 8 pi over 6, which is 4 pi over 3. Okay. And then multiply by a half again, and I would get 5 pi over 3. Okay. So then it looks like my solutions are going to be x equals pi over 3. Oops. 3's are not 3ing today. 2 pi over 3. And then skip to 4 pi over 3 and 5 pi over 3. If I did my next value, it wouldn't be 6 pi over 3. It would be 7 pi over 3. But that is outside of our interval anyway, right? Because it's bigger than 2 pi, so I don't care about that value. All right, so now I need to set up intervals with all those values. So fortunately, though, we just start at 0. So 0 to pi over 3, pi over 3 to 2 pi over 3, 2 pi over 3 to 4 pi over 3, 4 pi over 3 to 5 pi over 3, and 5 pi over 3 to 2 pi. Now we have to test all of those intervals. That's a lot. But we can do it. So again, my first derivative is, what was it? 1 plus 2 cosine 2x. Okay, well, I'm going to rewrite that here. And now I got to think about values to plug in. So I need a radian between 0 and pi over 3. I'm going to resketch a little unit circle right here to help us out. So something between 0 and pi over 3. What do you want to plug in? Could do pi over 6. You could do pi over 4, right? Those would be your two choices. You guys said pi over 6 first, so let's do pi over 6, okay? Now, I got to be careful. Like, this is not easy to do. So I got to plug it into this. So 2 times pi over 6 would be pi over 3, yeah? What is cosine of pi over 3? 1/2, good. So I would do 1/2. So if I write this out a little bit, f prime of x equals 1 plus 2, we said times a half. All right, well, either way, that's going to give me what type of value? Okay. What about between pi over 3 and 2 pi over 3? Pi over 2 is the only logical choice there. So if I plug in pi over 2, 2 times pi over 2 is pi. And you understand I'm plugging it into right here. That's why I'm getting these values here. So 2 times pi over 2 is pi. What's cosine of pi? -1. So 1 plus 2 times -1. 2 times -1 would be -2, right? So 1 minus 2 would be -1. So I would get a negative output there, okay? Now, between 2 pi over 3 and 4 pi over 3, so 2 pi over 3 and 4 pi over 3, what do you guys want to plus or test? Pi, yeah, okay. So if I plug in pi, pi times 2 is 2 pi. Cosine of 2 pi, whole revolution around the unit circle is going to give you a value of 1. 1 plus 2 times 1 is going to give you 3. I get a positive value, so it's positive there. So it's going to be increasing on that interval. Okay, between 4 pi over 3 and 5 pi over 3. Yeah, 3 pi over 2. Okay, so 2 times 3 pi over 2 is going to be 3 pi. Cosine of 3 pi is around the unit circle in half, which would be a cosine or an x value of -1. So -1 times 2 is -2. 1 plus -2 is going to give me a negative output. Okay, and then between 5 pi over 3 and 2 pi, I would probably test 7 pi over 4, TBH. So if I do 7 pi over 4 times 2, That would be 7 pi over 2. What is cosine of 7 pi over 2? So 7 pi over 2 is like 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2 would be down at the bottom, right? So my cosine value there is 0. Okay, so then I would have 1 plus 2 times 0, which would just give me 1, which is a positive value. Wow. Cool. All right, increasing. When x is an element of 0 to pi over 3, and from 2 pi over 3 to 4 pi over 3, and then from 5 pi over 3 to 2 pi. And then decreasing when x is an element of pi over 3 to 2 pi over 3. I forgot the union each time. Darn it. Unioned with 4 pi over 3 to 5 pi over 3. And then that's it. Just 2 intervals of decrease. Okay? Hey, that was the first derivative. Let's do the second derivative so we can find our concavity. The second derivative is easier, though. I promise. All right. Oh, I got to do blue. Okay, so now let's find our concavity. Okay, our first derivative was this circled equation right here. So I'm not going to lasso it, but that's our first derivative. So I need to take the derivative of that to get my second derivative. Okay, 1 goes away, and then I have 2 cosine 2x. So the derivative of cosine is negative sine, but I'm also going to have to multiply it by what? An additional 2. So negative 4 sine of 2x. Okay. All right. Now I need to set that equal to 0. I'm going to be careful about this. I mean, if I set it equal to 0, I'd get rid of that negative 4. Would you agree? I don't need that anymore. So I really just need to find when sine of 2x is equal to 0. So we employ the use of our friend, the unit circle. And I want to find, ignore the 2x, I want to find just where sine is equal to 0. Okay? Where does that happen at? 0, pi, 2 pi, and then beyond, right? I'll probably need those other values. So 0 pi, 2 pi, 3 pi, 4 pi, right? Go beyond our just one revolution of our unit circle there. Okay, so then 2x equals 0. 2x equals pi. 2x equals 2 pi. 2x equals 3 pi. 2x equals 4 pi. Divide each of them by 2. So I would get 0, pi over 2, pi, 3 pi over 2, and 2 pi. 2 of those values are endpoints of my interval. So I don't really need to set it up differently for the 0 and the 2 pi. But I would have an interval from 0 to pi over 2, from pi over 2 to pi, from pi to 3 pi over 2, and then from 3 pi over 2 to 2 pi. So only 4 this time. And I need to test by plugging it into my second derivative. Now again, this is not my second derivative, okay? This is my second derivative. So that's what I need to plug it into. If you need to rewrite it over here, just to remind yourself of that, negative 4 sine of 2x. The reason why I was so dramatic about that is because you divided out that negative 4. So that's going to change all of your signs, that additional negative, and it would mess up your concavity if you forgot to do that. Okay, so f double prime of x. Let's determine the sign. All right, what do you want to plug in between 0 and pi over 2? I'm going to do pi over 4. I'm going to go against what you're saying, and I'm going to do pi over 4. Here's why. 2 times pi over 4 is what? Pi over 2. So then what's sine of pi over 2? 1. I feel like it's an easier value to compute. You know what I mean? So then 1 times negative 4 is going to give me a negative value. All right, between pi over 2 and pi. 3 pi over 4. Yeah? So if I plug in 3 pi over 4, 3 pi over 4 times 2 is going to give me 3 pi over 2. What is sine of 3 pi over 2? Negative 1. So negative 1 times negative 4 gives me a positive value. Okay? Do you want me to show that so you guys can see where those values are coming from? I just don't want you to look back and be like, where did he get positive and negative from? What about between pi and 3 pi over 2? 5 pi over 4. Okay, so if I do f double prime of 5 pi over 4, I would get negative 4 times, okay, what is sine of 5 pi over, well, 5 pi over 4 times 2 is 5 pi over 2. So 5 pi over 2 would be north or south? I think it'd be north, right? Because you'd have 1 pi over 2, 3 pi over 2, and then 5 pi over 2 would be back up north. So what is the value of sine up there? Okay, so then I would have negative 4 times 1, which is going to give me a negative value. And then last but not least, between 3 pi over 2 and 2 pi, seven pi over 4. So f double prime of 7 pi over 4 would give me negative 4 times, okay, 2 pi times 7 pi over 4 is 7 pi over 2. Is that going to be north or south? So that'd be south, right? So that's a negative 1. So negative 4 times negative 1 gives me a positive value. So we would say our graph is concave up when x is an element of pi over 2 to pi, unioned with 3 pi over 2 to 2 pi. And then our graph is concave down when x is an element of 0 to pi over 2, unioned with pi to 3 pi over 2. Okay. Questions there? All right. That process is basically what you guys are doing. First derivative equal to 0, set up intervals, second derivative equal to 0. Now, the vast majority of examples we did were like easy functions, polynomials, right? Those behave nicely. I mean, we've done some wild stuff in this class. We've done some wild derivatives before. So once we start applying this to derivatives that are more difficult, then things get a bit more intense, okay? But we're going to start slow. Look how much work we did. Doesn't that make you proud, like looking how much we did? It makes me so proud. I think it's great. All right. Your homework is this. 231, you guys are going to do 1 through 16, 18 through 22, 29 to 33, 49, 55 to 58. Do you have to do all of them? No. I would do, a good amount and make sure you're comfortable with what we're talking about here. Okay? Like what would be good ones out of those? Well, yeah, use your judgment and look at the type of problems that you're facing. So like if you did a quadratic already and then the other one is a quadratic exactly like that, then maybe don't do that, right? But then if you see a cubic or something like that, like a different type of function, do those.
Are we having a quiz on this?
Your next quiz will be 4-1 to 4-3.
Next week.
Yes.
I'm trying to post it, bro.
We're going to be in this for a while, Rossi. There's 4-3 is going to take some time. 4-2, 4-3 is going to take some time. So.
He's like,
What are we doing on Friday?
I don't think Monday. Sometime next week. Not Monday, though. What are we going to do Friday when I'm not here? It's a great question, Soph. I feel as if we could probably use a little bit of supplement on chain rule. So I'm going to give you guys some sort of chain rule activity that you can work with together. And then I might have you guys watch videos on stuff related to this section from College Board. And maybe work on some other assignment together. I'm hoping that you guys will work well together when I'm not here and help each other out. That's what I'm hoping for.
Wait, when are you not gonna be here?
Friday. The thought of... It comes up?
Yeah, try to ask us to let.
Yeah, ask Miss to let us sub. She did it.
Dude, so in order to be a sub, you have to be like hired by the district in order to sub. She should be, right? I mean, she's still here Tuesdays, Thursdays. Honestly, if I posed that question to her, I would never do that because I want her to enjoy her retirement, even though she's still here all the time. But honestly, if I posed that question to her, she would 1000% be here on Friday lecturing you guys on this for sure. So I feel like I shouldn't, right? Like she's got to enjoy. Yeah, she's amazing and sensational. But I'm not going to ask her to do that. So.